In this review, I'd like to cover some special topics. This paper ultimately proved that all fundamental eyes are dynamic control systems. They control their refractive state to the average value of accommodation when the refraction is positive. Particularly, the eye changes in both directions when the accommodation system is changed. I'd like to give special credit to Antonio Medina, who's listed in the references. What is important is to determine the accuracy of the system. How accurately does the eye track or follow the accommodation system? This will be the result of analysis done in a study, and I will show that shortly. The study was conducted by Dr. Francis Young, Ron Berger, and myself. The goal of the study was to obtain a good, accurate estimate of the tracking accuracy of the system. The methods of doing this was the so-called ergodic hypothesis, and I'll explain that in due course. You start with the concept that you have two eyes, and they're driven by the same system, same accommodation system, same offset. And what happens is, while they follow the same visual environment, they develop differences in between the two eyes in terms of refractive state, left and right eyes. And this can be up to 1 diopter difference, which is totally normal. The method of measurement is simply to measure the left and right eye and calculate the difference, as shown by the data collected by Ron Berger. The result of this study was a difference of 0.213 diopters, RMS, and I'll show that in a graph. Here's the critical area. When you make a series of measurements on different individuals as shown, you can eventually show the time averages and are equivalent to the ensemble averages. This is the so-called ergodic hypothesis of statistical mechanics. I'm in complete agreement of this. So we then can use the value obtained by the ensemble and calculate to a time average. Here's the calculation. The differential is 213 squared, 0.213. So left and right eyes must be on the order of 0.15 squared, as shown. We can then show a time sequence showing the same noise and the same results. Here are the results. The goal of the study is actually to determine how accurate the system is. To get the first number of tracking accuracy, I would expect the future research could do a much better value than what we could do with the materials that were available to us. But this is definitely a start. I would like to see a study done where the value was more accurately determined. That will come in due course. Here's a statement of how you get tracking accuracy from the ensemble measurements. Accuracies are given in a number of ways. One is the probable error. It is obtained by multiplying 0.674 by the RMS value. The eye noise times 0.67 is probable error. The probable error in each eye was then 0.1 diopters, as shown. This is a positioning servo. It is not a defective device. It behaves as designed, and it's supposed to behave. I would expect that future studies will produce this type of result. In any event, it's intended to inspire more accurate measurements of the eye's accuracy by using this technique. Hope you enjoy this video. It's heuristic. It's suggesting ways of doing things, of getting right answers, of respecting the eye as the dynamic control system it always has been. Thank you so much.